Hello, everybody. My name is Vincent Ledvina, and I'm going to be talking to you about substorms today. This is a presentation that I gave for the Aurora Summit last year. The date of recording is January 1st, 2026, so Happy New Year. I'm just recording this now. I want to make sure that this presentation gets archived and that this sort of lives on past its expiration date. I gave this presentation during the Aurora Summit in person. It was about a 40-minute presentation, so I'm going to try and keep things to 40 minutes here today and tell you all about substorms, what they are, and how you can forecast them. The goal of this presentation is to be practical and to be actionable so that you can take what I'm telling you about now and actually apply it to your aurora chasing workflow and out in the field to improve your chances of seeing the aurora and your success rate. Here's a quick outline of my talk. I'll be giving you an introduction about who I am and why this is important. I'll talk to you about aurora science for a little bit. I'll talk to you about substorms, why they matter, forecasting them, and then end things off with some practical advice. And here on the screen is a video that I captured from Fairbanks, Alaska of a substorm. And this will be included in a blog article. And also I will say right off the bat that if you want to actually follow along, the presentation file along with sort of slide recordings like narrations and a blog post, as well as all this uploaded on YouTube, which is probably where you're watching it now. Everything's linked together. And so I'm trying to make this as accessible as possible. So if you find that listening to my voice and listening to this presentation in real time is not a great way for you to learn, there's also a blog post. There's also a slide deck, which you can chew through, which have narrations. So there's lots of different ways you can consume this presentation and get this education. So I'm just going to kind of gloss over this, but this was my fourth Aurora Summit. I grew up in the Twin Cities in Minnesota. Right before giving this talk, I actually met Dr. Akasofu at UAF, who doesn't really come into the office much because he's in his mid-90s, which is so impressive that he's still, doing science at that old age. But I met him, and he's really the person that, wrote the first seminal papers on substorms. So that was a really cool meeting that I had with him. There's me and Dr. Akasofu there. And yeah, I'm a space physics PhD student at the University of Alaska Fairbanks. If you are just meeting me for the first time through this video, really invite you to check out my website, theauroraguy.com. I run tours and workshops in Fairbanks. And my first time I saw the aurora was when I was 4 years old, back in 2003, the Halloween storms, growing up in the Twin Cities. And then I kind of rediscovered it when I was 16 years old through aurora photography. And then I was off to the races. So I've been just sort of all consumed by auroras. Some people call me the Aurora guy because this is really all that I do. I'm studying it, living it, I'm breathing it, and I love this stuff. So let's talk about a little bit of aurora science. If you're new to the aurora, you don't know much about aurora science, that's totally fine. I have a beginner's guide to aurora chasing ebook, which is available on my site, and there will be a QR code at the end of this presentation, which you can scan to claim it. It's a free resource as long as you sign up for my email list, but that email list gets you access to my aurora alerts, which I send out before any kind of big geomagnetic activity. So if NOAA Subsea forecasts a G2 or greater geomagnetic storm, I'll send out an aurora alert a couple days beforehand, or as soon as I can, to give you the rundown of what's going on and what you can expect for aurora possibilities, because SWPC doesn't really forecast geomagnetic storms with aurora chasers in mind. They care mostly about stakeholders such as power grids, aviation, people like that, people that need to know what's going on and need to protect society and our infrastructure. So just a little plug there. If you don't know much about aurora science, that's totally fine. We all start somewhere, but substorms are a good place to start. And I'll give you a little bit of background as to what all is going on in the context of auroras in the broader scope of the Sun-Earth connection. So the solar wind is a constant stream of charged particles from the sun, carrying with it energy and magnetic fields. It's kind of like a hot cup of coffee, and the steam off of the hot liquid inside the cup is like the solar wind coming off of the sun's atmosphere. So the sun is this, constant burning nuclear furnace, which just kind of, sloughs out this solar wind into space. And that flows out from the sun and bathes the entire solar system in magnetic fields and charged particles. And usually the solar wind is calm and gentle, but sometimes it can become gusty, which are when we have coronal mass ejections or solar storms, or blow faster than usual, which is when we have coronal hole high-speed streams. That solar wind is charged particles. With that carries a magnetic field, which has three components because we think in three-dimensional space. And so you can see there in the top right graphic, you have a BX, a BZ, and a BY. The letter B, as in Bravo, is just what scientists use to denote the magnetic field. So it's just like we use V for volts or I for current. B means magnetic field. And so the Z component of the magnetic field is really important because in the solar wind, if the BZ is pointing south, Earth's magnetic field points north. So if you have a north and a south coming together, just like bringing two opposite ends of a bar magnet together, those kind of stick together and that energy can be transferred between the two. So when you have BZ south, that just connects better with Earth's magnetic field. That's how the sun's energy and the solar wind can penetrate through and charge up our magnetic field. And we'll talk about that later. If this is like way over your head right now, really suggest you check out my free ebook, Beginner's Guide to Aurora Chasing. But this is what you need to know for now. There's a lot more to unpack, obviously, with space weather. It's a very diverse field full of hundreds, thousands, countless number of phenomena and concepts. But if you just know about the solar wind and the BZ and the fact that the solar wind can vary in strength, that's pretty good for now. When the sun gets angry, that's when the solar wind can become enhanced. So that means it can travel faster, there can be more particles, or it can have a higher magnetic field, stronger magnetic field, or that BZ could be pointing more south than usual. That means that the energy can flow in. So coronal mass ejections, or CMEs, are like sun sneezes of charged particles in the magnetic field into space. When they impact Earth, they can trigger geomagnetic storms. That's how we can get the auroral ovals, which are usually over the polar regions, the auroral zone, like Fairbanks, Tromso, Churchill, those kinds of places, to expand to lower latitudes. That happens during geomagnetic storms. Storms can last for days. Storms are not little blips in time like substorms. This is the main sort of differentiator. If you ever wonder what the difference is between a substorm and a storm is like a multi-day event, and a substorm is a quick 15 to 30-minute burst of activity. It's like if you're talking about a thunderstorm and you have a little hurricane inside that larger thunderstorm complex. By the time the first clouds get to you to the time the last clouds leave, it might be a few hours, but that tornado itself just lasts a few minutes. Coronal holes are like solar wind lighthouses, beaming fast solar wind into space. They are areas of open magnetic fields in the sun's atmosphere where solar wind can flow out freely. They can last for months and rotate with the sun every 27 days. They cause relatively reliable minor disturbances at Earth. I call them solar wind lighthouses because they are fixed in the sun's atmosphere. A CME is this quick puff of solar wind that, exits the sun, travels out into space. We can't forecast them. They just kind of happen spontaneously. Coronal holes are these large patches of open magnetic fields which allow the solar wind to flow freely. It's like taking a race car, like a Lamborghini, and moving it from, downtown Minneapolis to the Autobahn, right? It can just travel freely and just sort of max out its speed. It can go at its top speed. Same thing with wind. In active regions and in closed magnetic fields on the sun, the plasma is just bouncing in between in between the loops, the loop endpoints. So if I actually pause the video, you can see here, there's like these areas of bright magnetic fields or bright areas. That's where the plasma is really hot. Magnetic fields are closed, but if they're open, that solar wind just flows out freely, nothing to keep it bound to the sun's atmosphere. And that magnetic energy, isn't there. It just sort of flows out freely, so it goes faster. And so coronal holes, they rotate with the sun. The sun rotates every 27 days. So we get these fast streams of solar wind that just sort of bathe Earth, every 27 days roughly, as long as that coronal hole is still alive. They do eventually close up and they can change shapes and things like that, but they're pretty reliable sources of space weather activity. Earth's magnetosphere is like a protective bubble around us that protects us from the solar wind. It's kind of like we exist in a stream of water, which is a solar wind, and we're like a little rock. And that water just kind of flows around us. It creates a magnetosphere that doesn't quite look like a sphere, but more like a comet's tail. So The end that's facing the sun is pushed in versus the end that's not facing the sun. The tail is sort of extended out. The solar wind buffets around our planet like a rock in a stream of water, like I just said. And Earth's magnetosphere, shaped like a comet, side facing away from the sun, gets stretched out in a tail-like configuration called the magnetotail. Earth's magnetosphere is generated from that molten solid core. That's iron, that's metal, creates a magnetic field. Doesn't just stop at the ground, it extends out into space and forms this bubble around us. So Earth's magnetosphere is really important. That word magnetosphere is one that you're going to be seeing a lot in this presentation, but it's just Earth's protective magnetic bubble around us. And the solar wind can penetrate, that energy can penetrate our magnetic shield, our magnetosphere, again, if the magnetic field in the solar wind is pointing opposite of the field. So in sort of the most efficient case of that energy going in, that's with the BZ south. When the solar wind energy enters the magnetosphere via a process called magnetic reconnection, which you can start to see here, like that, it sort of breaks apart these field lines at the BZ south and encounters the BZ north. Those magnetic fields kind of separate and they start advecting, or I guess you could say convecting, around the flanks of the magnetosphere over the Earth's poles. And that starts stretching out the magnetotail. It's kind of like stretching out a rubber band. So when the solar wind energy enters the magnetosphere, the magnetotail stretches out. On Earth's night side, magnetic fields stretch and become unstable, eventually leading to a point where they come together, fuse, and reconnect again, and release pent-up energy in a large burst. So this entire motion of magnetic reconnection on the day side, followed by magnetic reconnection on the night side, is kind of like a breaststroke. You have this magnetic energy from Earth's day side that's being convected back towards Earth's night side, and it's storing all of this energy in Earth's magnetotail. This is just an animation of that. The sun is to the left in this animation. The aurora happens when energy from outer space traveling along Earth's magnetic field lines, that energy is primarily charged particles like electrons, enter Earth's atmosphere, encounter gases in our own atmosphere like oxygen and nitrogen, and energize those gases, creating different colors corresponding to different altitudes and different species being excited or ionized. The aurora occurs high up in Earth's atmosphere, around 100 to 500 kilometers in altitude, and red auroras are produced by atomic oxygen high up. Green auroras are produced by atomic oxygen around 100 to 200 kilometers, and blues are produced by nitrogen further down. You can get different colors like purple, like pink, different shades of red and, orange and things like that with color mixing. So if you have a particle that's coming all the way down, it has a lot of energy. It's going from outer space, has a ton of energy. It's moving down. It's starting to interact with different gases as it's going, kind of like a game of Plinko. It just donates its energy as it's going down. Each of these chemical reactions take around 3 to 10 electron volts of energy, but these electrons coming down from outer space have kilo-electron volts, so they're able to create lots of color as they're going down. So if you have a really energetic atom or electron, you have lots of colors. You have all the colors from red to purple on the very bottom. And so during a substorm, you have lots of particles. They have all sorts of different energies. So you have not only the greens, which are the most common, but you also have the reds and you also have the deep purples on the very bottom. So it kind of creates the full auroral curtain, which you can see. So what is a substorm? They're more or less aurora explosions. That's kind of how I describe them. You can see here, the aurora is a little bit static, and then it'll just all of a sudden erupt in a big explosion of light and color. Boom, right there, that's a substorm. And so what happens is you have this sudden change in the aurora. It kind of changes from this featureless arc, sometimes slowly drifting to the equator, sort of the equatorward side of the sky. In this case, this camera is in Ely, Minnesota, so you're looking north. That arc is slowly lifting up off the horizon, but then all of a sudden something changes. Boom, you get these pillars that form. Like I was mentioning, you have all these different particles of different energies coming down into Earth's atmosphere. They're energizing gases all along the magnetic field line, creating that gorgeous pillar of light and all the different colors in the aurora. And the thing just erupts from horizon to horizon, expands to the north. You have pulsating aurora following, It's the most beautiful part of the night of the auroral display is the substorm. Oops. And the substorm not only occurs, you can see it from one location, but it's really helpful to get a bird's eye view, or really like a spacecraft's eye view. So it's kind of like dropping a big stone into a body of water. You have this huge, deposit of energy that goes into the auroral oval, and it's sort of, there's that initial splash up, which you can kind of see this big auroral brightening, and then it sort of spreads out throughout the auroral oval. So you can see here, here's the auroral oval. I'll just pause it right now. Kind of over the usual spots. Like here's Churchill, Whitehorse is somewhere down here, Fairbanks is over here, Yellowknife is up here. This is around midnight for like, I think this is 7 UT, so it's around 2 a.m. Central Time or something. But you can see, the auroral oval is pretty good. It's in its normal spot. And then boom, all of a sudden you have this little activation here. That's sort of like you just dropped the stone in. You had that initial splash up. That's the start of that substorm. And then it spreads out throughout the auroral oval, and it sort of fills the entire thing. And then afterwards, you can see the auroral oval becomes much fatter and wider, and it's reached a much higher latitude, actually, which is interesting. But it's also somewhat expanded equatorward as well. If we go from here, let's see, like from right here, to right here, it's brighter, right? There's more aurora happening. This is sort of after the substorm, or kind of during the substorm expansion phase. There's more aurora, but it's also spread to different longitudes. Right now, it's all the way over Western Siberia, even spread out a little bit to like Greenland. And the auroral oval is much fatter, and it's expanded poleward. That's really important for the auroral expansion phase, which we'll talk about in a little bit. So the Earth's magnetosphere is like a giant rubber band slingshot. Energy from the solar wind is stored in Earth's magnetosphere. The tail region compresses and stretches out like a rubber band. What happens is you have the solar wind energy being, sort of charging up Earth's magnetic field with that BZ south. All that magnetic flux, those magnetic field lines are being stretched out, convected over the Earth's polar regions, and being kind of stretched out in this magnetotail like you're stretching out a rubber band. And so that's a really good analogy, because when that rubber band becomes too stretched out, it snaps. And if you've ever done the, experiment, or not experiment, if you've ever done the prank in grade school or middle school where you have a slingshot, you have a little piece of paper or something, and you're, pulling it back and you're launching it at the teacher or your friend or something, right? That slingshot in that little projectile is kind of like all the auroral energy that we see during a substorm. That magnetic field becomes too unstable, and it launches this stream of auroral particles, this energy from the magnetotail. If I just pause the video here, that's that point where that rubber band becomes too stretched and it snaps. There's all that energy, and it races along Earth's magnetic field lines to Earth's night side auroral oval. And so then you have the substorm there. The substorm comes in a cycle called the substorm cycle. It lasts around 3 to 4 hours on average. So from start of the growth phase to the end of the recovery phase, roughly 3 to 4 hours. This is all just, kind of back of the envelope stuff. It will vary from night to night, and we'll see some examples of that later. But the growth phase is when energy is building in the aurora. Typically in the aurora, that's when you have a really nice east-west, really defined discrete auroral arc that's slowly pushing equatorward. The expansion phase is when the best aurora happens. It's when that growth phase aurora just suddenly pops. You usually have some auroral beads before that happens as a sort of a quick signal to get outside and start looking, really paying attention, get the cameras, starting to shoot if, hopefully they already are at that point. But, and then the recovery phase is sort of the last part of that. The aurora needs to charge up, charge up again for another substorm expansion and growth and expansion. It's like you have a big battery, you charge it up for a long time, and then you run some really power hungry equipment, or you just sort of expend all that energy at once. You can't just immediately do that again, right? You still need to charge up that battery again before you can go through that next discharge cycle. So it's kind of like that with the aurora. You often, I don't think I've ever seen like 2 back-to-back expansion phases. Maybe your recovery phase is like an hour or 45 minutes at, really the shortest, but I don't think it's really possible to get 2, textbook expansion phases back to back, because the aurora just needs some time to recharge. Earth's magnetic field has to keep stretching out, has to stretch out again so it can build up that energy. The growth phase, in the aurora, you have auroral arcs align east to west, slowly moving equatorward, north to south in the northern hemisphere. And from a mid-latitude point of view, since I know a lot of people watching this are probably at latitudes or locations like Minnesota, Wisconsin, Michigan, from that point of view, you're not underneath the auroral oval, you're looking at it from the side. So you'll see an auroral arc if you're looking north, slowly lifting off the horizon. That just means that it's expanding equatorward because it's moving higher in the sky. It's moving more overhead for your, from your perspective. In Earth's magnetosphere, energy from the solar wind is charging up the magnetosphere like a battery. This happens most efficiently when the BZ is southward and the rubber band of Earth's magnetotail starts stretching. You can still get stretching and charging of Earth's magnetic field when you don't have BZ south. You don't need BZ south, but it really helps to have the southward pointing magnetic field, coming in contact with that northward pointing Earth magnetic field to get the most efficient energy transfer and charging up of that battery. The expansion phase is when a growing auroral arc suddenly springs to life with auroral beads, which turn into a fast surge of aurora expanding poleward. Bright colors and active motion occur. Auroral beads are just as they sound. They're like these little lumps of aurora that form along one of these auroral arcs, and they look like little beads or from, sort of the side, right? The aurora is not just a, one point in space. It's sort of a, vertically extended column or pillar. So you'll often see what kind of looks like a picket fence start to march across the auroral arc. That's linked to some sort of instability happening in Earth's magnetosphere. It's something that I'm actually focusing on for my PhD thesis. And that sort of starts off this chain reaction of the energy being released from this battery, if you will. It's sort of like, like flipping the switch, if you will, and like starting this whole like energy release. The exact reason why substorms initiate and occur, what triggers that is not known. Nobody knows exactly why this happens. It's like you can stretch out a rubber band, 100 times and it might give way, at different points, at every time. Sometimes it's just random. Sometimes you have to reach a certain critical threshold. It just all sort of depends on what the Earth's magnetosphere is feeling. There's a lot of preconditioning that's going on too. Like if you've already had a lot of substorms, maybe it's easier or harder to have another substorm. Or maybe if the BZ is pointing south for too long, the Earth's magnetic field just sort of gets into this, negative feedback loop, which we call steady magnetosphere convection, in which case there's no charging going on. All the energy just from the solar wind just goes right back into the aurora. So there's no stretching. So there's all these different sort of weird, quirky edge cases and things like that. And I'll talk about substorm initiation later and like what actually triggers the onset of an expansion phase, but there's really no way to predict it. So that's the question I get all the time is how can you predict one of these things to happen? There are some clues and some common things that happen in the solar wind, but yeah, it's really hard. So in the magnetosphere, what's actually happening during this expansion phase is that rubber band is snapping, the battery inside Earth's magnetosphere discharges energy quickly into the auroral oval, and yeah, there's no way to predict when this actually can happen. During the recovery phase, you'll often see some arcs sort of dancing on the northern horizon. We call those poleward boundary intensifications. That just happens. It's not a start of a new substorm. It's sort of just like the last gasp of the aurora before the pulsating aurora kicks in, and things just really calm down for the next couple hours. And pulsating aurora is really cool to see, actually. It's in my opinion, very underrated, but it sort of signals that you're in a recovery phase. So, if you're in Fairbanks and you see, let's say you've not been paying attention to the aurora and all of a sudden you go outside and there's tons of pulsating aurora going on, well, you probably missed the substorm. You're probably in a recovery phase and you have to wait for that next growth phase and expansion to happen so you know that something better is coming along. So, and that's one of those practical things I'll be talking about later too, is how to use the timing of the substorm phases to inform when you might pack it in for the night or when it's still worth staying out. And so usually the pulsating aurora fills the sky. The auroral oval might expand a little bit equatorward, but this gradually fades over the course of a few hours, and then the battery starts to recharge again. So, like a battery that needs to cool down, the magnetosphere simmers and vibrates with wave activity, causing pulsating aurora. After some time, it returns to a quiet state for another cycle. Every substorm develops differently. Here are two substorms, which start off very differently. They both, follow the same expansion phase and poleward expansion, but the sort of signs in the beginning of the growth phase are not the same at all. Like in case one, there's very faint aurora, but there is a very subtle east-west aligned discrete auroral arc. It's just so hard to see. And in case two, there's really bright east-west extended discrete auroral arcs, which are very obvious. And if you're underneath these, you don't know about a substorm and when it might take place. You might look at case one and say, oh, there's no way that the aurora is going to do anything. There's nothing in the sky. And you'd be wrong, because there actually is a little bit of aurora there, and there had not been a substorm recently. So we were in a growth phase, and you could actually see it. If you were looking at one of these webcams are really useful to be monitoring as well, because you can, especially if they're all sky cameras, because you can actually see where the aurora is, and you can use these patterns in the aurora to really tell when a substorm phase is, which substorm phase is occurring. But, if you're underneath that sky in case one, you're like, okay, well, there's no aurora, I'm just going to pack it in. Well, then you would have missed that gorgeous expansion phase with all the reds, really bright aurora, but it only lasted like 10 minutes. So you had to be outside for that. And then there was the pulsating aurora indicating the recovery phase right after. So, in case two, there's lots of aurora before the substorm. If you were out there, you'd be like, wow, the aurora is great. Maybe you would have no idea that something better was coming, but if you were out there, you were watching it, then you would have seen the gorgeous poleward expansion, super bright aurora that was, blowing out the all sky camera. And it was amazing, right? But you kind of knew that something was going to happen because there was already aurora there. And the expansion phase lasts a little bit longer too in that case. Every expansion phase is a little bit different. Some last 5 minutes, some last 30 minutes, and have like multiple sort of surges of activity. Who gets to see a substorm? Well, here's a picture of the auroral oval taken from a satellite, and you can see that's the classic auroral oval. Let's say a substorm occurred in that auroral oval. Well, the green line represents how far south someone could see the aurora without a substorm. The green aurora takes place at around 110 kilometers. And you can see that from pretty far away. I don't know the exact distance, but you can use some basic trig and figure out that something that's 110 kilometers in the sky can be seen from probably, 200 to 300, 400 miles away, right? When you're in Minnesota, you're seeing this auroral arc on the horizon over the northern horizon. That aurora is probably, over Lake Winnipeg or something. Like, it's really far away. So you can see the aurora from pretty far away, even if it's just green aurora. And that's pretty common, is that during a growth phase, and even during a recovery phase, you just kind of have green aurora. But during a substorm or during an expansion phase, and we use those terms kind of interchangeably, expansion phase and substorm. If someone says, oh, wait for the substorm, they're usually meaning to wait for the expansion phase, because that's sort of what we mean when we have a substorm. It's not necessarily the entire cycle. And it's sort of hard to tell whether or not we're in a substorm cycle or not. If we're just in like normal aurora, like not growth phase, not recovery, not expansion, versus growth, kind of hard to tell. So we just say substorm is the expansion phase. But during a substorm, the aurora becomes higher in the sky. You have more particles coming in with different energies. If you can just think of like a bell curve, basically lifting that entire bell curve and saying you have particles of high energies and low energies, which mean you can kind of fill out that entire auroral arc from the reds at the top, the low energy stuff, to the greens, and then to the pinks below, that really high energy stuff. That red aurora on the top can be seen from much further away because it's higher in the sky. So oftentimes if you're, a horizon chaser, somebody from mid-latitudes looking at the aurora, and you're waiting for the substorm, you might not see anything until that substorm happens and you see a little bit of a red glow on the northern horizon or the southern horizon. And you're like, wow, there it is. And the green is there. You're just too far south, too far north, too far equatorward to see it because the curvature of the Earth is blocking it. So during a substorm, those high altitude reds become more visible and brighter, and you can see them from further away. And so the auroral visibility extends rapidly equatorward during a substorm because of that. So during a non-substorm time, growth phase, recovery phase, maybe it's just the green line. But during that expansion phase for 15, 20, 30 minutes, when that aurora becomes very tall and bright, you can see it from so much further away. So if you're really trying to catch the best of the show, or the show at all, if you're at really far mid-latitudes, like even low latitudes in the US, and you're trying to catch the aurora, the only time you might be able to see it is during that expansion phase. So that might be the only time you can see it at all. Why do substorms matter? Kind of just mentioned this, but if you're seeing the aurora all night, the substorm will be the best part. It's the bright and dancing aurora, many colors are visible, easily can overpower the full moon. And if you're waiting to see the aurora, a substorm can just give you that chance. If you're really far from the aurora oval, like Colorado, a substorm may provide you with a brief window to photograph the aurora on the horizon. So even if it's not visible to the eye, it could be visible on your camera, right? We all know that cameras can see more than our eyes can. The aurora is actually there. It's just that our eyes cannot take a long exposure like a camera can. But this is really cool because this is a photo I found from Twitter, used with the permission of the photographer, showing aurora in Burlington, Kansas, photographed during a substorm in November 2025, even visible during a supermoon, so even a brighter than average full moon. The aurora was visible at this low latitude because of the substorm. You can only really see the red colors, right? That's the high altitude, low energy particles that are causing those reds. And they were visible on a camera. And that's really cool because that was the only time of the night when that person could see the aurora, was during that brief 10-15 minute window of that substorm expansion phase. Forecasting substorms. How does Earth's magnetosphere get charged up for a substorm? Well, first, the solar wind's magnetic field needs to be oriented in a way that can transfer energy into Earth's magnetosphere. BZ South is the best for that. Earth's magnetic field flows north or positive. So when BZ South in the solar wind comes in contact with Earth's magnetic field, the field lines reconnect and energy can transfer in. Reconnection starts the process of charging up Earth's magnetosphere. Earth's magnetosphere is like a rubber band. As reconnection forces energy in, the magnetotail loads up with energy and charges. Earth's magnetic field stretches out and the tension starts to build. That's that energy building up, the battery getting charged up, ready to release that pent-up energy in one of these substorm expansion phases. What triggers the expansion phase? BZ turnings might actually trigger expansion phases and the onset of a substorm. After some time of negative BZ, when you have the battery charging up, a sudden switch to positive can be just like, again, flipping the light switch. You quick kind of shift the conditions that can cause things to destabilize, and boom, you have the release of all that energy. Shocks too. If you have a CME that impacts during a growth phase, that might just trigger an expansion phase right there and then. But most substorms are triggered spontaneously and we really can't forecast when they occur. So it's not so much forecasting substorms, but rather it's tracking them. And that's where I think the GOES magnetometers is one of the best tools for tracking substorms. If you don't know what the GOES magnetometers are, I have a blog post about them on my website, and I actually go into further detail and sort of simplify things in this new substorm blog article that I'm releasing with this recording and with this presentation I'm moving through with you now. But you have two satellites that are geostationary, so they're rotating with the Earth. They're over North America. GOES East is over the US East Coast. GOES West is over the US West Coast. So if you're a chaser on the eastern coast or sort of central eastern US, you want to be using GOES East. If you're in Alaska or on the US West Coast, you want to be using GOES West. And these only work for North Americans, unfortunately, because they're geostationary over North America. The lines, these magnetometer plots that you're seeing here on the top right, are the standard data product that the GOES satellites release. They basically measure how stretched out Earth's magnetic field is. So lower values equals more stretched, equals more charge. If you see the line really going down, it's charging. If you see it spiking up all of a sudden, it's releasing. And because the satellites are naturally moving in and out of Earth's stretched magnetotail, remember Earth's magnetosphere is always like this comet shape, the lines naturally follow this sort of sinusoidal pattern throughout the night. So, over the course of the night, you will start seeing those lines just naturally moving down. But when it's really diving down fast, that's when you know that magnetic field is stretching out really quickly and that charging is happening. So you can imagine that the GOES magnetometers are, they're essentially measuring this distance here, indicated by the white arrows. It's measuring the stretch of Earth's magnetic field. So when you see that stretch drastically reduce, it's like taking a rubber band and quickly, basically, you have a stretched rubber band, it's much shorter in height, it's more stretched out. So that sort of value of the white arrows is much less. But when you suddenly release it and it becomes more of a circle, becomes more dipolar, that value as measured by those white arrows is much higher then. So when that happens very quickly, that's that magnetic field and that rubber band quickly letting go and dipolarizing, as we call it, and releasing all that energy. Using the GOES magnetometers really only works when it's nighttime in North America. Just mentioned this, but East Coast should be using the red line, West Coast should be using the blue line. The graphs naturally oscillate every day because they move from the day side to the night side. So, you'll have the satellites on Earth's day side magnetosphere when North America is in the sunlight, because the Earth rotates, but the magnetosphere stays the same, right? Same thing with the auroral ovals. We are rotating underneath the auroral ovals. The aurora is not rotating above us. It's a kind of a weird thing to think about. It's just like you see the stars rotating in the sky. It's because Earth is rotating. It's not because the stars themselves are rotating, right? And so because of this, the curves always decrease around nighttime, but the sharp decreases indicate the substantial charging. So here's what that actually looks like: a geostationary satellite, and the Earth is rotating, and the satellite is staying fixed above a location on Earth as it's rotating. So goes east and goes west, those locations never change. So Earth is rotating, which means these satellites in space are rotating through different regions of Earth's magnetosphere over time. So here's a nice little example. During the growth phase, indicated in green, as the rubber band stretches, the curves go down. This usually happens when self-BZ is occurring and can take multiple hours for that charging. During the expansion phase, the graphs spike. The height of the spike is not constant from substorm to substorm. So that's important too, is that people ask me, well, how much should it spike? And the start of the spike looks like the start of any spike. But when you really see it starting to go, that's when you're really noticing, oh, wow, there's a lot of energy being released. But it could just be a little release, and like you threw a little rock into a stream of, or into like a little pond of water. But if you're right underneath that initial splash, you're going to see that substorm. It's going to look amazing. But if it's a really small rock, it's not going to ripple that far out into the auroral oval. So it may be that there is a spike in the GOES magnetometers, but that substorm is not traveling out in longitude as far. But if you have a really big rock, a really huge spike, a really big release of energy, you drop it into the pool of water, you inject that energy into the auroral oval. It's a huge injection. It just massively spreads out, and you can get those substorms, which might happen in the East Coast, traveling all the way, East Coast of the US, all the way to like Alaska, right? And so that big spike up is the expansion phase. The recovery is basically everything after that until you start to see the graphs start to go down again. Another substorm could charge right after, but usually the plots will start to slowly decrease or flatline to a slow rise. Remember, there is that natural oscillation. So if you do see it start to go down, but it's very, very gradual, or it's just sort of flatlined, that means that you're in recovery. There's not much charging taking place. Does GOES mag really work? Well, the aurora brightens within a few minutes of the spike, but it depends on where the satellite is relative to the substorm. Actually those particles being launched from Earth's magnetotail, where that's actually happening. It's like, if you're in a river, right, there's parts of the river that are flowing faster than other parts. So if you're standing in a really shallow area, the river might not be flowing that fast. You're like, wow, this river is not very strong. But you walk 2 steps forward, and all of a sudden you drop 5 feet, and the current's like moving 5 times as fast. Same thing with the substorm. You might have this broad injection of particles, kind of like a river, and there might be little fast injections within that broader envelope of moving energy. So if the satellite's not in that really fast injection, it might not see a huge spike, but in reality it is happening. It's just the satellite's not there in space to measure that. So that's one of the problems, or I guess not problems, because it's just what we have, but it's a limitation of using the GOES magnetometers and a lot of these tools, is that you're only sampling 1 point in space or 1 point on the ground, whereas the substorm is taking place somewhere on Earth and starting to propagate and move throughout the auroral oval, and it's just a matter of where the sensors are to pick up those disturbances. So you might see the aurora brighten up a little bit after the spike, a little bit before the spike in the GOES magnetometers. It's not that they're not working, it's just that maybe the substorm was not directly on the satellites. It was a little bit off to the side, and it just kind of had to spread out, or the satellite had to move into that stream of particles to sort of get that reading. And so what you've been watching is an example using one of the webcams in Maine. The green line indicates the time of the aurora in the video, and you can see that basically during the spike in the GOES magnetometers, you see the substorm, you see the red pillars, particles of different energies, lower energy particles extending the height of the aurora, further visibility equatorward. I believe this substorm was seen down in like Pennsylvania, right? So the actual aurora is taking place very far north of even Maine, but it's so high up in the sky that people in Pennsylvania are able to see it. There are a number of apps that you can use to track substorms, including the Glendale app and Norley's. There are limitations to both. Some of the pros of Glendale is that it works around the world, and whereas GOES-Meg just works for North America. It's very accurate as well, and it can catch substorms as soon as they start. That's really important because substorms don't last that long, so you want to get outside right as soon as you know a substorm is about to happen. Norley's is nice. It shows you a really nice graphic of an auroral oval with brighter green where there's more substorm activity. And it has a graph too, which you can kind of track things, but it starts responding to substorms a little bit, not necessarily too late, but with a small delay. So by the time that graph is showing a huge spike, the substorm might already be a few minutes in. So you might miss it by a few minutes, but that's okay. You're still getting the best show. You just might not be out and watching the entire thing from start to finish. My favorite thing is to track substorms with webcams. You can look at the different phases, the growth, expansion, and recovery. And the best way of knowing what the aurora is doing is to see a picture of it in real time. Obviously, there are also limitations to using webcams. You only have a view of the aurora where you have a webcam, right? But the aurora is happening all around the world. So if you don't have a webcam to watch what the aurora is doing, the aurora is still there doing something. You just don't have a view of it. So you're kind of getting an incomplete picture sometimes if your webcam is clouded out or you just don't have a webcam where you want to look. But it's still great to have a network of webcams all around the world to monitor things. When you see the aurora going crazy, you have the auroral beads, you know a substorm's happening and it's time to get outside. Don't track substorms using the KP. It's too slow to respond. It's a global index, so it doesn't track structure within the oval. Ovation is also not suitable because it's a model, so it never represents anything that's actually happening. It's just an estimation. And it's only trained on incoming solar wind data, so there's a lot of physics missing, right? I was talking about how, we don't really know what causes substorms to trigger. It's not necessarily everything with the solar wind. This is totally, totally glossing over the fact that ovation is a historically trained model. So it won't even get these BZ turnings. It doesn't know what that means, right? It's just looking at what kind of solar wind is coming in, how much aurora power should that equal, and then it just fluctuates based on what the solar wind's doing. It doesn't take into account the charging of the battery, for example, or the different phases of the substorm. That's not what it's designed to do. So, it's also only trained on incoming solar wind data, so it's missing the preconditioning of Earth's magnetosphere, what happened before the current solar wind that it's looking at, right? Doesn't know any of that. It doesn't take that into account. So, lots to say about ovation. It's a great tool, but it has its limitations, and those limitations are unfortunately not known by much of the aurora chasing community. And ovation was never designed to be used for aurora chasing. It's just a measure of, incoming or an estimation of the precipitation of electrons. So that doesn't necessarily always correlate to what actually is happening and also what matters for auroral visibility. So this is just one example. Great substorm in Ely, Minnesota on this webcam. KP was a 2, ovation said 18 gigawatts, but we have aurora, and that was seen down in the Twin Cities in Minnesota. So just goes to show you, and this happens all the time, right? That the KP and ovation don't align with what's actually happening in the aurora. So some practical advice: knowing the substorm phase tells you where to point your camera. Arcs that move equatorward north to south indicate a growth phase. Expansion phases occur spontaneously, but the furthest auroral arc to the equator usually brightens first and moves quickly poleward. Closest sunset and closest sunrise, the aurora brightens first from the west and east respectively. This is because of, just kind of simple logic. If you have a big stone dropping into a pool of water, if you're on the right side of that stone, the ripples are coming at you from the left, right? Or from the west, and vice versa. Same thing with the substorms. And there's actually a preference for that aurora to be traveling westward as well. Westward traveling surge is what that's called. So based on this, you can point your camera facing northeast in the evening and then northwest in the morning. You may still miss some of the aurora, but that gets most of it, right? That's sort of the most efficient way to do things. So this is just one example, is that to capture this time lapse, I knew that the brightening usually comes in the south and pushes north during the expansion phase. That's a poleward expansion. And so I faced my camera east because and not to the south, and leaving a lot of room to the north as well. So I kind of was like angling it northeast kind of because I knew that when that substorm happened, it was going to be coming from the east. This is also during the evening, so it was going to be a westward traveling surge coming from the east, moving overhead, and also expanding poleward. So I was able to get all the aurora basically. I didn't miss anything, and that's really nice because when you're out in the field, you got your camera set up for a time lapse. You're like, okay, what the heck is the aurora going to do? Am I going to miss it? Is it going to go completely overhead and totally out of frame? Because at high latitudes, you're not just facing north with a 35 and you're like, okay, great, I have everything, right? The aurora is happening all around you, and you have to know which arc or which direction to really be paying attention to. So don't just face north and expect everything to happen in front of you, right? The aurora might move overhead, that's that growth phase, and then ignite overhead and then push north. So it's kind of nice to be angled either northeast or northwest, depending on the time of the night, to get that poleward expansion. You can actually, show that motion in the expansion phase. That's really, violent, active, vigorous, right? In a time lapse, you want to show the aurora evolving, moving. That's one of the beauties of time lapse, right? So making sure that you're taking into account the substorm phase, which direction to face your camera, that will make your shots much more compelling. Knowing the substorm phase also tells you when to pack up or when to stay out longer. Growth phase is stay out. Something could happen at some point. There's no reliable way to tell when a substorm will occur, but you know that something better is going to happen. So packing up during a growth phase, if you haven't already seen a substorm, right? If it's 10 p.m., you're like, oh my gosh, I don't know if I should stick it out for another hour. The aurora's like not doing anything, even though I see this auroral arc. It's just, totally boring and featureless. You know that that's a growth phase, right? Let's say you take a picture of it at 9:30, you take another picture of it at 10, take another picture of it at 10:15. You scroll back through your photos, you're like, oh, that arc is getting higher in the sky. That's a growth phase arc. You should stay out because something is going to happen. You just don't know when, but something will happen, probably, right? Maybe not will happen. There's never absolutes in science, but 99% of the time, right? There is at least one substorm per night. Usually there's a substorm every 4 hours or something. So that's about 6 substorms a day. A night is roughly, 9 to 12 hours. That's, at least 2 substorms a night, 1 to 2 substorms a night. If it's really quiet, maybe just 1. Usually in Alaska, there's like 2 to 3. If sunset's at 8 p.m., sunrise is at, 5 or 6 a.m., usually 2 to 3 substorms. And then, yeah, if you see a growth phase, something better is going to happen at some point. You want to stay out. You see the expansion, boom, amazing. You're like overjoyed. You've seen it. You're satisfied, and then you see the recovery phase, and you ask yourself, should we pack up? Well, substorms can recharge fast during active conditions, but usually it takes a couple of hours. So maybe it's time to go to bed. You can get your sleep. There might be a better substorm later in the night, but at least you've seen something. You've seen one of the substorms, and you've seen at least one of the best times of the night, if not the best show of the night. So if you see a substorm, the main message is head outside because it is time to watch the aurora. It's time for things to get active. Amazing. It's really hard to put it into words. I'm sorry, I'm just struggling there because I'm watching this video. This is one of the best auroras I've ever seen. This was March 5th, 2022 in Fort Yukon, Alaska. And this show blew me away. It was the one that really changed my perspective on everything, including the aurora. It was just almost a spiritual experience, just overwhelming. And you really have to see one of these. You really have to see a substorm, preferably at high latitudes too. It's right overhead. It just feels like you're being transported to another dimension. But if you see a substorm, head outside and just enjoy the show. And with that, thank you so much for listening to this presentation. My email's on the screen. Please email me with any questions, comments, feedback on this presentation, any way that I can help you. That is my goal. I want people to see the aurora. I want to do everything I can within my power and resources to do that. And so also join my email list. QR code is up on the screen now. Take out your phone, scan that, sign up. I have my free ebook, which will be automatically emailed to you, along with you will be signed up for my aurora alerts, which I send out whenever there's big geomagnetic activity coming. So if you're at mid latitudes, you don't want to, follow space weather every single day. You just want to know when you should start paying attention. This is a great way to sort of get only the necessary information, only when things are really good, right? I mean, I don't send an email out every single night, but I send out emails whenever it's worth it. So hopefully this presentation was helpful for you. It had some practical advice in it. Recording this a little bit after my in-person talk, but it still is relevant knowledge. And I'll be updating things, over the course of the year in 2026 with just better analogies, more practical advice I can think of, because substorms are super important. It's like integral that you understand this for effective aurora chasing. You can be outside the entire night and you can see everything, or you can be an efficient aurora chaser and understand what's actually going on so you can make better decisions, and you can get sleep when when you can get sleep and when it makes sense to get sleep. You can reposition to a new location when you're in a recovery phase so you don't miss any aurora. You can face your camera in different directions so that you're capturing the entire show. There's a lot that goes into substorm knowledge that you can apply to the real world, which I think is really cool. And that's what I want to focus on, is how do we take the science, which I think is super cool. Not everybody thinks it's super cool. I understand that. But how can we take the science, the knowledge, how to track the behavior of the aurora, recognize patterns? How can you take all that and really apply it to the real world and make a difference in your life? And so I think that, hopefully this presentation communicated that a little bit. But with that, I'll sign off. Thank you again for your attention, and I will talk to you all later. Bye.